Welcome, Pure Maths 3 students. This is week 21 of our maintenance. First question this week is going to be a logs and exponential functions question, and we are asked, well, obviously the word hence here suggested it was part of another question. What am I probably meant to do? Okay, I think I'm going to take the log of both sides, so just log base 10 of both sides. So I could rewrite as my first step 3x minus 1 using the power rule there, log 4, log base 10 4, right, equals, and then I can separate these ones out, log, using the multiplication one, so log base 10 3 plus x log 5, okay? Just think about your log rules there, and that's how I've done that. I guess the next line I could go 3x log 4 subtract log 4 equals log 3 plus x log 5. Now what I probably want to achieve at this next point is get the x logs across to one side. So this one and this one need to be on the same side so I can factorize to get the x out. So probably what I'll do is I'll go 3x log 4 minus x log 5, and then I'll bring that log 4 across the other side, so I get log 3 plus log 4. You can see I can now factorize, so I'll go, maybe x, and then into 3 log 4 minus log 5 equals, and I can simplify that side to log 12. And I don't actually have to solve this exactly, but I can write it as x equals log 12 divided by. Now what I'm going to do, just to practice my log rules, I'm going to rewrite this. I'm going to say that's like log 4 cubed is 64. Take away log, so log 64 take away log 5, which is like log 64 over 5. Now if I chuck that into the calculator, what do I get? When I did this just before is 0.975. Okay, so good to review and make sure you're trying to practice those log rules. Now the next one is a identity that we have to prove. So you can see that we've got a 2 theta and a 4 theta here. So we're going to use the double angle rules, I think. That's probably what I want to do here. So my first step will be to work with this one here, cos 4 theta. So I can write that as 1 minus, should be 2 sine squared 2 theta. Okay, that's that one. And the next one will be minus 4, and then that one would be 1. Oh, what can I do here? Because, maybe I'll use this time cosine squared theta minus sine squared theta. Okay, what I'm trying to do is I'm trying to get to a state where I've got this here, the sine to the power of 4 theta, and I'm thinking that's going to come out of this one here when we change that, because that's we can use double angle rule to change that. So that's probably going to be my first move. Now in my second move, I'm going to go 1 minus 2, and then I'm going to go, what can I do here? Well, I can use the double angle rule. So I've got sine 2 theta, and then it's also times sine 2 theta. I'll come back to that. Minus, and then I can just say, well, this is like 4 cosine squared theta minus 4 sine squared theta. Okay. Now, remembering your double angle rule for this one, okay? So you know that sine 2 theta is equal to just 2 sine theta cosine theta. So what we're going to have in the next line is 1 minus 2, and then it will be 2 sine theta cos theta, and then squared, take away, and I've got the same thing here, 4 cosine squared theta minus 4 sine. Oh, so that should have been a plus. Oh, sorry, whoops, not there. When I expanded it wrong. It should be plus, shouldn't it? 4 sine squared theta. Because a negative times a negative. This negative times this one. Wake up, okay? Alright. And so my next line is going to be 1 minus 2. And what do we get here? So I guess we get 4 sine squared theta cosine squared theta when we apply the power there, sorry. So this will be 4 cosine squared theta here, plus 4 sine squared theta. Yes, okay. So what we're going to do now is we're going to expand this bracket. So we're going to go 1 minus 2, 8 sine squared theta cosine squared theta minus 4 cosine squared theta plus 4 sine squared theta. Now what I can do is use another identity with this one here, and this is how I'm going to get my sine to the power of 4. So I'm going to go 1 minus 8 sine squared theta into, now cosine squared theta is like 1 minus sine squared theta, isn't it? From Pure Maths 1. So that's our next line. I know I'm doing this very slowly, bit by bit. Okay, so we get 1 minus 8 sine squared theta when we expand this bracket, plus 8 sine to the power of 4 theta minus 4 cosine squared theta plus 4 sine squared theta. Now I've pretty much run out of room there, so we'll bring everything over to here. Now, what have we got here? I think we're doing pretty well. I think what we want to do at this point is change this into a sine squared theta. So what we'll get then is 1 minus 8 sine squared theta, because we're trying to get rid of the sine squareds, aren't we? Plus 8 sine to the power of 4 theta minus 4 into 1 minus sine squared theta. So I'm changing that cosine squared theta into 1 minus sine squared theta plus 4 sine squared theta. And now you can see, well, we're pretty much there. 1 minus 8 sine squared theta plus 8 sine 4 theta minus 4 plus 4 sine squared theta plus 4 sine squared theta. Now, let's have a look. These two guys cancel out that one, and then the 1 minus 4 is negative 3, so we end up with 8 sine to the power of 4 theta minus 3, which is what we were trying to prove. We are done. Now, maybe there was an easier way of doing it, but I think, well, we got there in the end. That's the main thing, isn't it, really? Okay, now hence solve the equation, and this equation is what we had up there. Oh, and then the plus 3 is added to it, plus 3. Okay, so what are we going to do for this? Well, if we're adding 3... Wait, oh, wait, hang on. Sorry, what have they done here? Sorry, it's not the same. So... Okay. Let's just take this one here and then try and get what they've got. So, another way of writing what they've got here would be cosine 4 theta minus 4 cos 2 theta minus 3 equals something. Now, you can see that this bit here is what we've got here. But since we've subtracted 3 from it, we need to subtract 3 from the other side here. So we can rewrite the whole thing as 8 sine to the 4 theta minus 6, okay? And we can say that is equal to 0. So I hope that makes sense to you. Just have a bit of a think about what I've done there. Now, we can rewrite that to 8 sine to the 4, excuse me, sine to the 4 theta equals to 6. And I go sine 4 theta equals 3/4. Take the square, the 4th root of both sides, and it's going to be plus or minus the 4th root of 3/4. Now, what do we get when we do this? Okay, I'm getting the values theta equals 68.5. So if we just quickly sketch our graph here, this is our 90 degrees here, 180, 270, and so on. So at the 4th root of 3/4, positive 3/4, you're going to get this one. So you should have another one over here. So we're just going to take 68 off 180. So that should give us 1.5. And now let's do the negative 4th root. And that gives me 291.5. Well, actually, I get something over here and I add 360 to get it. And then if there's one there, should also be one here. So you just go, what is the, how far is it from 360? And it's going to be the same amount from 180, so add that on. So I'm getting 248 for that, 0.5. We should be fairly proficient at solving these, I think, now. It's just the first bit, really, isn't it? Using the double angle rule to get it into a form that we can solve. That's a bit new for us in Pure Maths 3. Okie dokie. Now, moving on, what have we got here? We're trying to differentiate a curve with this equation. Okay. So you can see that we have to use the quotient rule, isn't it? Don't we? So I'm going to say that u is equal to ln x. I'm going to first of all I'll first of all just deal with the top because that's a bit more complex. So I'll say du dx is equal to 1 over x. And then, so I'm using chain rule here, just to work out what it would be when I differentiate that top bit before I use the quotient rule. Okay, so y equals u squared, so dy du should be equal to 2u, and therefore we can say that dy dx, if I'm fully differentiating that top line, is going to be equal to, just the top bit would be 1 over x, so it would be 2 ln x over x. Okay, so that's what it is when I differentiate the top bit. Now we can try the whole thing. So we're going to use the chain rule. It's going to be the quotient rule, v du dx minus u dv dx all over v squared. Now, for this second component, so u equals ln x squared, and therefore du dx is what we found over here, okay, is equal to 2 ln x over x. Now v is obviously the bottom line, which we've got x, and so dv dx is just simply 1. So now we go ahead and pop in all of that data. So we get v, which is x, times du dx, so 2 ln x over x. Then we go minus u. Now u is ln x all squared times 1. So we can just put that there. And at the bottom we've got v squared, so x squared. Now you can hopefully see we can cancel that and cancel that. So we're going to get 2 ln x minus ln x all squared all over x squared. Okay? Now, the next part is we've got two stationary points and we find the exact values of the coordinates of these points. Okay. Just maybe drag this over to here. Okay, now if we want to find the exact values of the stationary points, what we're going to do is we're going to take this top bit here and set it equal to 0. So at the stationary points, dy dx is equal to 0, and therefore in this case the numerator has to be equal to 0 because it's the only way you can make 0. So we set this equal to 0. I can factorize, of course, like that. So our two x values are going to be x equals 1 because ln x is 0, isn't it? Sorry, ln 1 is 0. And then the other one would have to make, in the bracket we have to make it x equal to e to the 2. And that would make that bracket equal to 0 because ln e to the 2 is 2. And 2 taken away 2 is 0. So those are our two values. And therefore our y values, we can just chuck them into the original equation here. Now if we chuck in a 1, we'll get 0. And if we chuck in an e to the 2, we're going to get ln e to the 2 over, what will that be? So that will be 2 squared, so 4 over e to the 2. So I think it should be like this. So those should be our two values. Just chucking them into here. So the coordinates are 1, 0, or e to the 2, 4 over e to the 2. There we go. That was a bit tricky, wasn't it? Okay. Well, now we're going to try and find doing integration, find the exact value of this. This is, of course, our old favourite, the integration by parts. And it looks to me like we might have to do it twice. So I'll start off by saying u is equal to x squared. And so du dx must be equal to 2x. And I'll say that, therefore, the other one is dv dx, which is sine 2x. And therefore, v is going to be, now what would that be when we integrate sine 2x? It'll be negative 1/2 cosine 2x. Is that right? Just do a backwards check. Yeah, that's right. That's good. We are good. So that's our first step. Okay. Now we're ready to roll. So we'll say so we should have, so this is going to be equal to now what's our remember our rule for this. So it's going to be uv minus integral of what is the rule? Just having a brain fade here, team. What is it? Minus integral of v du dx. I'm pretty sure that's what it is. I don't know why I'm forgetting things. Okay, so that's what we want to do here. And we can chuck in our limits at the end, I think, is what I'm going to do. So now, if it's uv, we should get equals, let's do it up here, equals x squared, so u, multiplied by negative 1/2 cos 2x minus the integral, we'll apply the limits at the end, minus the integral of, now what have we got here, 2x multiplied by negative 1/2 cos 2x. Now next line we can simplify this as negative 1/2 x squared cos 2x minus, and I'm going to put a bracket here, this would be the integral, oh we don't need a bracket just yet, hey, hold your horses, minus the integral of, that'll be negative x cosine 2x. So this bit here, now we're going to have to do the same thing again. So we're going to have to integrate by parts again. So I'm going to say u is equal to negative x. So du dx is therefore equal to, hang on, have I done that right? Maybe? Okay, yeah, no, that's alright, we'll do that. Is equal to minus 1. I'm just wondering if it might have been easier to define it slightly differently. And then we can go, so dv dx is equal to cos 2x. And so v is equal to 1/2 sine 2x. So I think that's good. Okay, so that's my second little bit of info, and perhaps we'll move things over to this other side here. So we should have equals negative 1/2 x squared cos 2x minus, and then this whole thing I'm going to put in brackets. So I'm going to do uv, so it's negative x times 1/2 sine 2x minus the integral of, now I'm going to go negative 1, so du dx times v, which is times 1/2 sine 2x. And so the next line is negative 1/2, oh dear, negative 1/2 x squared cosine 2x minus, now I'm just going to leave this bracket open for a moment, negative 1/2 x sine 2x minus, now I'm going to pop this next thing that I'm integrating, so I'm going to go up to cosine 2x, so it should be 1/2, and I think it should be positive, yes. Okay, now we can start expanding all of those brackets. So we get negative 1/2 x squared cosine 2x plus 1/2 x sine 2x. Now that minus 1/4 will become positive when we times it by the minus outside the square bracket. So it should be plus 1/4 cos 2x. Now, we're finding the exact value, so we can chuck this whole thing in. So it's going to be minus 1/2 x squared cos 2x plus 1/2 x sine 2x plus 1/4 cos 2x, and then we're putting in our values of between 0 and pi over 2. Okay, so what does this give us? Right, if we put, so the first one I'm going to put in the pi over 2. So we're going to get minus 1/2 bracket pi over 2 all squared. Now, cos pi over 2 is, oh sorry, it won't be cos pi over 2, it'll be cos 2 times pi over 2, which is pi. Now cos pi, if you think about your cosine graph, is going to be negative 1. So we'll times it by negative 1 there. Plus 1/2 times pi over 2. So that would end up being pi over 4, wouldn't it? Pi over 4. So pi over 4. And then sine, so the sine pi is going to be 0, isn't it? Times 0, so that will just drop out, plus 1/4, and then that'll be cosine, so that'll be times -1 again. So that's our first bracket. Maybe I should have, right, put it in a bigger bracket like that. Then I put in my lower limit, so you can see that because you've got a 0 here, that'll get rid of that, that'll get rid of that, so you're only going to be left with cosine 0 at the end, 1/4 cosine 0, which is simply 1/4. So it should be like that. Now when we just chuck this into the calculator, we're going to get, well, we can actually just do it in our heads, can't we really? Pi squared over 8 minus 1/2. And perhaps we can even factorize that. 1/8 pi squared minus 4. And we're done there. Alright, well that was a bit long and complicated. Now we're going to do this next one. We're going to expand in powers of ascending powers of x up to x cubed. That should be x cubed. Whoops. So I would rewrite this first as 1 minus 2x all to the power of -1/2. Okay, that's my first step. And then we can say, oh, that's equal to 1 plus, and then it would be minus half times -2x, so it's just x, plus minus 1/2 to minus 3/2 over 2 factorial into minus 2x to the power of 2, and then obviously we're going to do the last one, which is going to be minus 1/2 times minus 3/2 times minus 5/2 all over 3 factorial. It's getting a bit messy, isn't it? Times minus 2x to the power of 3. Now we're going to get 1 plus x. Now the next one, positive 3 over 8, and then times 4, so 1/2, 3/2 I think, plus 3/2 x squared. And then next one, 2, 4, 8, 16, 48. And then, oh, hang on a second. Yeah, 48. And then we go, divide that by 8, so 6. 15. Okay. No, use the calculator. And we have 5 over 2x cubed. Alright. So yeah, always check with the calculator anyway. Last one for the day, I think, is it? No, I seem to have missed out. I think I've missed out one of the questions, so let me just go hunting for that, because I see it now. Well, that's interesting. I thought there was another question in your sheets here, which is not in mine anymore. So I don't know if that's disappeared from your work or not. Yeah, I really don't know what happened to that. I hope I didn't accidentally delete it or something. It was a algebra question, finding partial fractions, but it's not. I can't find it anymore, so I'll just go straight on to the vectors question. Maybe I deleted it for some reason. Okay, so what have we got here? We've got points A, B, C have position vectors. Here's our position vector OA, OB, OC, and D is such that the quadrilateral is a parallelogram. Okay, so if we think about that, so we're going to have something like this. A, B, C, D. Okay, A, B, C, D. Okay, there we go. So this is our parallelogram, really poorly drawn. Okay. So these are position vectors, and we're trying to find the position vector of D and verify that it is a rhombus. Okay, so first of all, we could say that BA equals CD. If it's a parallelogram. So first of all, I'm going to say what BA is. So BA should be equal to B to O plus O to A. So, or A take away B, right? So when we do that, we're going to get B to O. So we get I, and then we've got 2J take away 4J, so it should be minus 2J. And then looking at our K's, 3 take away 1, so it's just plus 2K. Now, if that's what B to A is, therefore, C to D should be the same. And if you want to know the position vector of D, so O to D equals O to C plus C to D. Now we know what OC is because we've been given that up here, and we also know what CD is, so we're just going to add these together. So when I do that, I get 3I plus 3J plus K. There we go. Now, if it's a rhombus, so we've got the position vector. If rhombus, then we know that AD equals CD, or BC equals CD. Okay, now, so let's find CD. So CD equals, and we can take the vector that we've just found here and find the modulus. So it's the square root of 3 squared plus 3 squared plus 1 squared, which is 9, 18, 90, square root 19, I think. Is that right? Oh, wait a second. That's not CD. That's the position. That's the that was the position vector of D. I want to take not that. I want to take this. Wake up. So it should be 1 squared plus minus 2 squared plus 2 squared. 4, 8, 9. So that's equal to 3. Now let's do BC. Okay, BC. Now I have to find out what BC is first. So I'll do that here. BC is equal to B to O plus O to C. So C take away B. B to O, O to C. So that would be, where's O to C? Okay, so we're looking at up here. So I think it's 2 I plus J minus 2K. And therefore, when we do the modulus of it, it's going to be the square root of 2 squared plus 1 squared plus minus 2 squared, which also gives us a 3. There we go. So, yes, it is a rhombus because the sides are equal. Okie dokie. Last one is differential equations. And what have we got here? There should be a bracket here. For some reason that's dropped out. The variables x and theta satisfy this differential equation. It's given that when x, okay, so we're given a parameter here which we can use later. what am I going to do here? Okay, my first step is I'm going to get that d theta across the other side. So I'm going to go 3 plus cosine 2 theta dx equals x sine 2 theta d theta. And then I'm going to go dx equals x sine 2 theta. So I'm separating my variables, or working towards that, and then I'll have it over 3 plus cos 2 theta. Now I need to get rid of this jolly x here, so I'm going to divide both sides by x. So I've separated my variables at this point, like that, with 3 plus cos 2 theta d theta. Now I'm going to integrate both sides. So I'm going to integrate this and integrate this. So I should get ln x on the left-hand side. And when you look at that right-hand side, you can see that this is also going to be ln, because you've got a situation where you've got this, something like this. Okay, so I think it's going to be negative 1/2, and then ln 3 plus cosine 2 theta, and plus c. Now let's just quickly check this. So if we were to differentiate this, differentiating inside that bracket there would give you negative, negative 2 sine 2 theta, but what you want is actually positive sine 2 theta, so that's why we've got this half business here, negative half, because it gets rid of the negative 2. Yep, I think we're good there. And so I'm now going to use the parameters that they've given me here. So I say ln 3 is equal to negative 1/2 ln 3 plus cosine, and that would be 2 lots of theta, so it would be pi over 2 here, plus c. So we get ln 3 plus 1/2. Now, because I'm moving that across. Now, ln cosine pi over 2 is 0. So it'll just be 3 here equals c. So that's what c is. And so therefore we've got this formula ln x equals negative 1/2 ln bracket 3 plus cosine pi over 2. 2 theta. Sorry, that was a parameter. I can take that out there. The 2 theta plus, and then we know what c is now, 3 over 2 cosine. 3 over 2 ln 3. You might be thinking, how did he get 3 over 2? Because, when you use your ln rules here, your log rules, you're going to multiply 3 by 1/2. Sorry, step back. That's not right at all. What we've got is 1 times ln 3, and then we've also got 1/2 times ln 3. So altogether we've got 1 here and 1/2 here, so that's 3 over 2. There we go. That's what we're doing here. Sorry guys, wake up. All right. Now what we can do at this point to get our final answer. Wait a second. I think that's actually all we need, isn't it? I guess we could perhaps simplify it a little bit, couldn't we? We could perhaps go, because they're both times by sort of a half kind of thing. Maybe we could say minus 1/2 ln blah. So that bit. And we can go, well, this is like plus 1/2 ln, and then that would be 27, because we're just taking a 3 out there, so we're cubing that 3. And then I guess we can say it's kind of like the square root of, and then on top we're going to have 27. So we can go ln 27 over, and then 3 plus cosine 2 theta. So using the log rules there, we've got a positive log, take away a negative, so we're just going to, with the same base, so we're just going to pop that over the 27 over 3 plus cosine 2 theta. And then we can get rid of the logs from both sides because we've got it in the form of log something equals log something. So therefore we can say x is equal to the square root of 27 over 3 plus cosine 2 theta. Now, the next step is we've got to state the least value taken by x. Okay, so the least value occurs when the denominator has its max value. So let's look at 3 plus cosine 2 theta. Now, the greatest value it can be when cosine 2 theta equals 1. Okay, because you know with the cosine graph, the greatest value you can get is at 1. So therefore, greatest value when x equals the square root of 27 over 4, which is equal to the square root of 27 over 2, which is equal to square root 9 square root 3 over 2, which is equal to 3 square root 3 over 2. That's the least value taken by x. Right, I hope this has been helpful to you guys. It seems like a long one to me, or maybe I'm just tired doing this. Hope it's been helpful. If there are any errors that I've made, please let me know so I can fix them up. Okay, take care. God bless.